This is Aidan Tarble for the class of EGR 214, Numerical Methods for Engineers, and this is a presentation on what Simpson's rule is and how we can use Excel to make the Simpson's rule a little easier. Now, the idea behind the Simpson's rule is that we want to approximate the area under a curve, given an analytically impossible function like the integral of e to the sine of x. And this function is not possible analytically because there's no method we know of that can solve it. You can't do integration by parts, you can't do a substitution, you can't do anything with it. But this method is especially useful when you already have x and y data because the formula requires information about certain x, y points. Now, if we look at that graph, we can take some point on the graph and go some delta x distance to the left and right, and continue doing that across the whole line, which will give you some points like this. Now, from those first 3 points, we can come up with an equation for the parabola that is on all 3 points, since any 3 points in space can have a parabola connecting them. Now, we'll make more parabolas along the curve that go along the entire curve. Now, if we bound those parabolas, we can take the definite integral of those parabolas, which gives us an approximate area under that curve. And the idea behind it is that the larger our delta x value is, the less precise we get, because there are less parabolas giving us a less precise curve. So we want that smallest delta x value as possible to get the most precise graph. So theoretically, if we could have an infinitely small delta x and an infinitely large amount of parabolas, we would have an almost exact approximation of that area under the curve. Now, in order to actually use this information, we need to derive some sort of formula. So we'll start with a general formula for the area under a parabola. So that's given here as the definite integral of the standard form of the parabola from negative delta x to delta x, which gets us this kind of weird equation at the bottom. Now, if we solve for 3 y values of the first 3 points, negative delta x, 0, and delta x as our x values, plug those in, get our y values, and we see that our first y value plus 4 times our second y value plus our third y value gets us something that's close to what we had before. Now we plug that in, we can find this general area for any curve if we just take the area of multiple parabolas and add them together. Now in Excel, we can use that example from before, e to the sine of x, and we can create an xy table with the x values ranging from 0 to 6. We have a set change in x or delta x value that's calculated as b minus a over n, where b and a are the bounds, 6 and 0, and n is the amount of steps, so 8. Next, we can plug in the y values by using our function exp of sine of x, which means e raised to the power of sine x, and the x value of the function is given in the adjacent cell. We can fill in this equation for all y values by clicking that small square at the bottom right corner of the cell and dragging it down to the bottom cell. Now, we can enter in the formula that we derived earlier and choose the data from our table as the y values in our formula. Once we press enter, we can see our approximate area being incredibly close to the actual area. And you see it's very, very close. And here you can see the margin of error is only 0.08%. So very, very close. And the idea is that, if you had a smaller delta x, that margin of error would be even smaller. Now, you can use this in the real world with something that's like an area of something very obscure and hard to calculate. So here we can see an oddly shaped swimming pool, and we can actually use the Simpson's rule to determine the area. The width measurements are given there, our y values, and they were measured every 150 meters, so that's our delta x value. Once we plug all that into our formula, we get an approximation of the area of the swimming pool. Now, in conclusion, the Simpson's rule is a good way to approximate areas when the exact area is not known and cannot be found through integration. The method works by generating parabolas along the curve and using sets of 3 points, and the smaller the distance between those points, the more accurate the area is. By using Excel, we can easily implement the Simpson's rule by generating a step size and a list of xy points and plugging that into the formula. The method has practical real-world applications that aid in finding areas of irregular shapes. And all in all, the Simpson's rule is a powerful numerical integration tool that simplifies the most complex area calculations, and using Excel can make it both practical and highly accurate.